Topic: motion in a circle. We will be looking at uniform circular motion, and what we'll do is we'll go through some definitions, and then we will look at the physics of it, okay, the physics of uniform circular motion, the concepts and so on, and then we'll look at some calculations. Now, when we deal with uniform circular motion, look at this note I've made here. Think of motion in a horizontal circle. So when we deal with uniform circular motion, we are talking about an object moving in a circular path at constant speed. At constant speed, very important, yeah? So how do we visualize this? Think of a, let's say, rubber ball. Okay, we tie it at the end of a string, and then what we do is we whirl it around. Okay, whirl it around in a horizontal circle. Again, we have a rubber ball. Okay, this is a rubber ball, yeah, and what we do, we tie it at the end of a string, and then we whirl it around in a horizontal circle. Okay, this will be an example of uniform circular motion. So let's draw a picture here, what I'm trying to get across to you. Okay, this is the center of the circle, this is the string, and this is your rubber ball. Okay, rubber ball, and then we whirl it around in a horizontal circle. To whirl means to turn. Okay, so this will be your direction of motion. Okay, so when you whirl this around in a horizontal circle, we say this is an example of an object exhibiting uniform circular motion. Very important. It is an object moving in a circular path at constant speed. First, let's look at two important terms: angular displacement and angular velocity. So keep an eye on this picture as we go through some definitions. Now, angular displacement, theta, it is the angle swept through about an axis of rotation through O. This is the center O. Let's say we have an axis, okay, going through this point O perpendicular to your screen. Okay, and this particle here is in horizontal circular motion. Great. So again, yeah, it is the angle swept through about an axis of rotation through this center O. Now, theta here, the angular displacement, is measured in radians. Okay, in short we write RAD. Now you have to know that pi radians is 180 degrees. Okay, we know that. Let me write it somewhere else. We know that 2 pi radian is 360 degrees. Therefore pi radian is 180 degrees. Now you need to know this definition, very important. Yeah, how do you define a radian? Now, 1 radian is the angle subtended at the center of a circle by an arc length which is equal to the radius. Okay, again let's read this. Yeah, very important definition. How do you define a radian? 1 radian is the angle, that's important, is the angle subtended at the center of a circle by an arc equal in length to the radius. What does this mean? So let me draw a picture here. Okay, let's say this is the center. Now let's say the radius here, let's give it a number 3 cm. Now this arc length here, let's say, is 3 cm. So therefore this angle here will be 1 radian. That's the point. Okay, so the arc length is equals to the radius. Okay, when the arc length is equals to the radius, we say that the angle that is subtended here is 1 radian. Now 1 radian is about equal to 57 degrees. that's not a big deal because we know pi radian is 180 degrees, so you can easily use a calculator and work out the fact that 1 radian is approximately equals to 57 degrees. So this definition here, okay, I have drawn a picture here to show you. We have an angle theta here, and we have a radius r, we have an arc length of s. When s equals to r, then theta is 1 radian. We have motion in a circle. Let me write it here. We have motion in a circle. Therefore, we have theta, the angular displacement, is changing. So when theta is changing, we can have a rate of change of theta. Okay, great. That brings us to the next definition. We want to talk about omega, the angular velocity. The angular velocity is defined as the rate of change of the angular displacement. Okay, now we like to write it simply as omega equals to theta over t, or in more mathematical form, if you like, d theta dt, the rate of change of angular displacement. Now I will use angular speed and angular velocity interchangeably in my videos. Okay, just remember that for us omega is constant, it is unchanging. Okay, please take note, omega is the angular velocity and the units radian per second. Okay, omega is given as radian per second because theta is measured in radian, time is measured in seconds, so we have omega measured in radian per second. Now again, let me remind you, omega for us will be constant, and I will be using the words I'll be using the words angular speed and angular velocity interchangeably.